Okay, so today we're going to talk about environmental management in MPI, which is the subject of Chapter 9 of MPI Standard. And this is going to be episode number 38 of Learning by Doing MPI. And it's going to be basically the same drill as always. We start this chapter, we go with 24 to 25-ish minutes of content. And after every 24, 25 minutes, we're going to break it down and start up a new episode. And I have no idea beforehand that how many episodes we're going to have for this chapter. But yeah, we're going to go along and see what happens. Okay, so we do have a couple of examples. So this chapter is not a lengthy chapter. It's actually a very brief chapter. And we are not going to cover parts of this chapter, and I'm going to tell you the reason when we reach those areas. And I have tried to write a couple of very simple examples for this chapter. As you can see, unlike other chapters like collective communication, or even the chapter about virtual topologies, which we had so many examples, in this chapter we don't have so many of them. Okay, so we start with environmental management. Let's see what this chapter is about. This chapter discusses routines for getting and, where appropriate, setting various parameters that relate to MPI implementation and the execution environment, such as error handling. The procedures for entering and leaving the MPI execution environment are also described here. So the first sort of subject is implementation information, and that is version inquiries. In order to cope with changes to the MPI standard, there are both compile time and runtime ways to determine which version of the standard is in use in the environment one is using. The version will be represented by two separate integers for the version and subversion in C. You can use, you see the pattern like hash define. So these are like macros. And we already had a dedicated video to macros in C++. If you haven't watched that and if you don't know what macros are, please go back, refer back to that video, macros in C++. So one version is basically using macros. So you see we have version and also a subversion, two separate integers. This is the standard 4.1, and of course these variables are set to be 4 and 1, and we don't care about Fortran. And there is another way to do that without macros, and that is through some standard functions like MPI get version, which you can see you basically feed in two variables. In this case, both of them are integers, int stars. You get to pass in the address of them, of course. And you get version and subversion, which represent the version number and subversion number. We do have one example for this one, MPI version inquiry. So let's take a look at that. So let me check if we have something else here. We do have something else. So let me talk about this function in the standard, and then we take a look at this example. So MPI get version, which gets two sort of arguments, and then both of them are outputs actually. So MPI get version can be called at any time in MPI program. This function must always be thread safe, as defined in section 11.6. We haven't talked about this chapter yet. Valid MPI version and subversion pairs in this and previous versions of MPI standard these are the valid versions. So we have 4.14, 3.13, 2.2, 2.1, and etc. Again, the same example is here, MPI version inquiry. So this is the next sort of routine, MPI get library version, which again, you pass in two arguments, version and result length. Version is going to be, it's an output. It's going to be populated with the version number. You see that it's saying that it's a string, and it's sort of a char star string, sort of a CS style string. And result length is actually the length in printable characters of the result returned in version. So what this one does, MPI get library version. This routine returns a string representing the version of the MPI library. The version argument is a character string for maximum flexibility. And this is an advice to implementers. We don't care about that. The argument version must represent storage that is MPI max library version string characters long. So you got to pass in this as to be safe, sort of. And MPI get library version may write up to this many characters, which is this MPI max library version string, into version. The number of characters actually written is returned in the output argument result length. So the actual numbers which are written into that variable is sort of represented by result length. In C, a null character is additionally stored at version result length, of course, because this is how basically C works with text and characters. The value of result length cannot be larger than MPI max library version string -1, of course. In Fortran, we don't care about Fortran. Let's pass that. And then we have MPI get library version can be called at any time in an MPI program. This function must always be thread safe as defined in section 11.6, which we said we haven't talked about that chapter yet. We are at chapter 9, and we just passed virtual topologies, which was the subject of chapter 8. Okay, from here we have a different sort of example. So we go back. So these things, I'm not going to comment on them. You already know what they are. So the first one basically shows using macros to get those version inquiries, And then we have like an if statement here. And this is, by the way, is done by not all the processes that we have in our MPI program, but this is only with the root process will do that. So we check. These if statements are very similar to what we have in C. So we check if the version is 4, and if the subversion is greater than equal 1, then we print root actually prints MPI 4.1 or later is detected. If the version is 3, the major version is 3, then we say that 3.x is detected. And if the major version is 2, we say 2.x is detected. And other than that, we say that, hey, your MPI version is actually too old. Or using the standard function, we need a version and a subversion. Both of them are integers, and you got to pass in an interstar, that's the address of version and the address of subversion. And then you pass it in MPI get version. And then root process basically prints the same information that we basically did with the help of macros. And then finally, we had this MPI get library version. You need to, the reason I put it C version is because that I already used version as a variable. So we use C version. And then as sort of the length of this array, we put this MPI max library version string. This we already talked about it in the standard. And then we had we need also an integer. We pass in those parameters into this function. And root process, again, basically takes us from there and tries to print sort of the MPI version info as follows. Very simple example. So MPICC MPI version inquiry. And I'm trying to run it. That's 8 processes. So you see that this is the first one. The first output is with the help of macros. We said MPI 4.1 or later is detected. And then with the help of sort of standard functions, we got MPI version as being 4 and MPI subversion as being 1. So this is the standard 4.1. And then finally, this is sort of the information that we get out of MPI get library version, that you see that it's actually a very long string. So you see that MPICH version is 4.2, and then release date is printed here, and also these are the configure sort of things. And if you haven't watched the compilation of MPICH, so this is how I configured my MPICH. We disabled sort of Fortran, and then we used a custom installation directory. So it also prints all sorts of information, and you can see that we don't have any Fortran also for this MPI version. So very simple. The first set of stuff is basically finished. Now we move on to the second portion, which is environmental inquiries. We do have an example for this one, that is MPI environmental inquiries. So let's take a look at that. So let's see. I need to remember what things do we have here. Okay, now I remember. We have basically 3 things that we need to discuss. So when using the world model, a set of attributes that describe the execution environment is attached to the communicator MPI com world. when MPI is initialized. So when we are using sort of MPI init or MPI threads init and stuff like that. The values of these attributes can be inquired by using the function MPI get attribute described in section 7.7. So if you haven't watched chapter 7 video, which was about the one before virtual topologies, which was about groups, contexts, communicators, and caching in MPI, please go back and if you don't know what MPI get attribute is, please go back and watch that sort of video series as well. It is erroneous to delete these attributes, free their keys, or change their values. So this is the list of predefined attribute keys that we have. So this is why I said that we need to discuss three things. One is, or the first thing is the tag upper bound. That is the upper bound for tag values. Then the next thing is MPI IO. Don't worry, we're going to have a lengthy description down here for tag values and then for IO rank and stuff like that. So this is the shorter version. MPI IO, rank of a node that has regular IO facilities, possibly my rank. Nodes in the same communicator may return different values for this parameter. Okay. MPI W time is global Boolean variable that indicates whether clocks are synchronized. When using the sessions model, only the MPI tag upper bound attribute is available to you. Vendors may add implementation-specific parameters, such as node number, real memory size, virtual memory size, and etc. These predefined attributes do not change value between MPI initialization, MPI init, and MPI completion, MPI finalize, and cannot be updated or deleted by users. Okay. Note that in C binding, the value returned by these attributes is a pointer to an int containing the requested value. Okay. So the required parameter values are discussed in more details below. So the first one was tag values. Tag values range from 0 to the value returned for MPI tag upper bound inclusive. These values are guaranteed to be unchanging during the execution of an MPI program. In addition, the tag upper bound value must be at least 32,767, which corresponds to the value of 2 to the power 15 minus 1. An MPI implementation is free to make the value of MPI tag upper bound larger than this. For example, the value of 2 to the power 30 minus 1 is also a valid value for MPI tag upper bound. Okay. In the sessions model, the attribute MPI tag upper bound is attached to all communicators created by MPI create from group and MPI intercom create from groups. Again, these things, are flashbacks to chapter 7, which we talked about, groups, contexts, communicators, and caching in MPI. With the same value on all MPI processes in the communicator. In the world model, the attribute MPI tag upper bound is the same value on all MPI processes of MPI world, MPI world. Okay. So this is the first one, tag upper bound. The second one is IO rank. The value returned for MPI IO is the rank of a processor that can provide language standard IO facilities, which means that for Fortran, that all Fortran IO operations are supported, such as open, rewind, and write. And for C, this means that the ISO C operations are supported, like fopen, fprintf, and lseek. If every process can provide language standard IO, then the value of MPI any source will be returned. Okay. Otherwise, if the calling process can provide language standard IO, then its rank will be returned. Otherwise, so this is the third scenario. Otherwise, if some process can provide language standard IO, then the rank of one such process will be returned. This is another scenario. And then the same value need not to be returned by all MPI processes. If no process can provide language standard IO, then the value of MPI proc_null will be returned. Okay. This is advice to users. Note that input is not collective and this attribute doesn't indicate which process can or does provide input. Okay. Then the last thing we need to know is clock synchronization. The value returned for MPI W time is global is 1 if clocks at all MPI processes in MPI.com world are synchronized, 0 otherwise. A collection of clocks is considered synchronized if explicit effort has been taken to synchronize them. The expectation is that the variation in time as measured by calls to MPIW time will be less than 1/2, less than, actually, this is a typo in the standard, 1/2 of the round trip time for an MPI message of length 0. Okay. And if time is measured at a process just before a send at another process just after a matching receive, the second time should be always higher than the first one. The attribute MPIW time is global need not be present when the clocks are not synchronized. However, the attribute key MPIW time global is always valid. This attribute may be associated with the communicators other than MPI.com world. The attribute MPIW time is global has the same value on all processes of MPI.com world. Okay, so we have seen these three sort of aspects, and now we jump into the example. So here, these things, again, we don't need them. We have already talked about them like billion times already. And then again, we have an isolation if here because only the root wants to print some stuff. The first category of things that we are interested in is the tag upper bound. We are going with sort of the flow in the standard. We don't want to talk about these variables that we have defined already, but we're going to see when we are going to use them. So of course, for tag upper bound, we need this tag upper bound here. And this sort of function MPI get attribute also needs a flag. That is why we supplied a flag here. And here, MPI get attribute, it gets a sort of communicator, and it gets this is sort of a predefined value, MPI tag upper bound. And then we pass in, so this is, if you remember, we had key and values, like, those pairs of things. And this is sort of the things that we are looking for, the thing that we are looking for. This is a predefined value, MPI tag upper bound. And then we pass in this tag upper bound to get the value corresponding to this sort of key. And then we pass in the flag. And then we put an if, of course. If everything goes fine, then the root basically prints the upper bound that MPI tag upper bound is actually this value. And then you need to dereference it because we defined it as a sort of, what's it called? As a pointer, as an int star. And also notice that tag upper bound is an int star, but here we passed in actually the address of that int star. So this thing is should be actually a void star, I think, what we have in MPI get attribute. Okay. The next thing is, so we print here the upper bound, and then MPI IO, MPI get attribute again, and we ask for MPI IO. This is another attribute, another key that we are asking for the value, and then this is the variable that we have here, star IO. This is an int star, and then we pass in the same flag. We don't need to define different flags, and then we use again with this if flag if everything is okay. Then we had these sort of three scenarios that we had. MPI any source, this means that all the processes basically can provide standard input output, and if the IO corresponds to MPI proc null, it means that no MPI processes basically can provide a standard IO. And then else we say that, hey, this MPI IO is the rank of the process which can basically have a standard IO. And then the final thing on the line is MPIW time is global. And that is, again, we use this MPI get attribute and we pass in our communicator. Again, we pass in the key, and that is MPIW time is global. And then we pass in the variable here, which is also, again, an int star, W time is global. And we pass in the same flag. And then finally, we print whether our clocks are synchronized in our MPI processes or not. So there we go. Again, a very simple example of the syntax and semantics of these environmental inquiries. So let's do an MPICC MPI environmental inquiries and run it with 8 processes. Then you see that this is the tag upper bound. So this is the value I get. I think last time I checked it, it was 2 to the power 28, if I'm not mistaken. So we're going to check that. Let's go with Chrome, online calculator. So 2 to the power 28 is 268435, 268435, 455, 456. Okay, so this is 2 to the power 28 minus 1. And you saw in the standard that at least it should be 2 to the power 15 minus 1, which is 3276, 7. And let's show that one too, to the power 15 and minus 1. This is 32767, the value in the standard. So in my case, on my system, this is actually 2 to the power 28 minus 1. And then every proc can provide standard I/O. So the result of that was basically MPI any source, the result of this check right here. So the value which was returned with this MPI come get attribute for I/O was actually this MPI any source. So we know that all the MPI processes are able to do a standard I/O. And then finally we have the W times global is false or is 0. Okay, so now we basically move on to the next topic, which is inquire process name. So we have an example for this one, MPI hardware resource info. Let's just jump back. MPI hardware resource info. We do have a couple of things here. We have MPI get process name, and we have MPI get hardware resource info, and MPI info get n keys, and MPI info get nth key, and MPI info get. So some of this stuff you're going to see in the standard, but part of them you're not going to see them. But let's go and see how this one goes. So this is MPI get processor name, and it has two arguments, the name, which you see that it's an output, and the result length, again, it's an output. You see that the name is actually a CS-style string, and the result length is the actual length, similar to what we had before, which we used that predefined max sort of value to construct our array. Sorry. So again, here result length is the real length, the imprintable characters. And then name is a unique specifier for the actual as opposed to virtual node. Okay. This routine returns the name of the processor on which it was called at the moment of the call. The call is a character string for maximum flexibility. From this value, it must be possible to identify a specific piece of hardware. Possible values include processor 9 in rack 4 of mpp.cs.org and 231, where 231 is the actual processor number in the running homogeneous system. The argument name must represent storage that is at least MPI max processor name. Again, we do have this predefined sort of max value to basically populate the array for the name. So MPI get processor name may write up to this many characters into name. The number of characters actually written is returned in the output argument of result length. In C, a null character again. So these are the same stories as before we had. So the result length cannot be larger than this MPI max processor name -1 as well. In Fortran, we don't care about that. And then we have a rationale here. This function allows MPI implementations that do process migration to return the current process. Note that nothing in MPI requires or defines process migration. This definition of MPI get processor name simply allows such an implementation. Okay, we don't care about this one. We haven't talked about process migration. And there is something here, but though, advice to users, the user must provide at least MPI max processor namespace to write. Okay, we already know that one as well. So, whoops, 24 minutes mark is over. I'm going to finish this example and then we're going to continue in the next episode. Of course, these things we have seen a billion of times. And then again, we need this result length and then the sort of character array. We populate it with this maximum process name, and we use this MPI get processor name. We pass in name and result length, and then the root process basically prints the name of that thing. And then the next thing is actually inquire hardware resource information, which is sort of the next thing on the line. So let me basically compile this because we want to finish this episode and go to the next one. Let's at least see the first portion of things that we need to see. And you see that the process name actually is Einstein 2. This is the name of my basically laptop, the name that I used for my laptop. That is what is basically at least returned when I use it on my personal computer. But then you're gonna see a different sort of information when you use it on an actual cluster. When you're working with, at a supercomputing center, or if you are in a company, then you have your dedicated sort of supercomputing center and stuff like that. So that's how you can use this sort of function, MPI get processor name. So we're going to continue in the next episode. I don't want to make this one lengthy.